In this section, we're going to talk about concavity and the second derivative test. Before we go ahead and look at examples, let's first make sure that we know what concavity means. So our definition of concavity is, first, let f be differentiable on an open interval. And remember that in order for a function to be differentiable, it must also be continuous. We're going to call this interval capital I. And then the graph of f is concave upward on I if the derivative is increasing on the interval, and concave downward on I if f prime is decreasing on the interval. Notice that this is not the same kind of increasing or decreasing of our original function. It's the increasing and decreasing parts of the derivative function. So let's take a look at a couple pictures. Notice that in this picture, if I were to go through and label all the parts where I have positive slopes of the derivative function, that this is indeed an increasing function because all of my slopes are positive. So in this case, we call this concave up and increasing. And if I were to look at this next picture, I see that my slopes are all decreasing here, like so forth. So this is an example of a concave downward function, and it is because f prime is decreasing. So this is what concavity means. It's just whether the graph has an upward shape or a downward shape. So this leads us to talk about, well, how do I know in the intervals in which a function is concave upwards or downwards? And that's what the second derivative test helps us do. The first derivative test, remember, helped us find the places where a function was increasing and decreasing. This test takes it one step farther to determine whether the function is concave up or down. So here's what it says. First of all, f is a function whose second derivative exists on an open interval, which we call I. So if we look at number 1 here, it says if f double prime of x is greater than 0 for all of the x values in that interval, then f is concave upward in that interval. And the same goes for if f double prime is less than 0, then everything is concave downward in the interval. So let's take a look at an example that applies this rule. So let's take a look at this example. This is in your textbook on page 191. It's on page 191, and we are going to skip a few of the steps because the steps are in your textbook. So the first thing that we want to do is take the first derivative of this function, which we can use the quotient rule or the chain rule. It's your choice. But for f prime, I should get negative 12x over x squared plus 3 squared. So in order to get the second derivative, I take the derivative of this, and that will yield f double prime, as we say, to be 36 x squared minus 1 all over x squared plus 3 cubed. So the goal here, just like in the first derivative test, was to see what happens when we set these equal to 0. So that's what I would do here. So let's set this equal to 0, and if our values for x are less than 0, it's concave downward. If it's greater than 0, it's concave upward. So here's what we're going to do. When I solve this for x, I get x is equal to 1 and negative 1. So we're curious to know what happens in between 3 intervals in particular. So I'm going to kind of set up my intervals here. So the first one I'm going to have is from negative infinity all the way up to negative 1, because that's my first x value right here. My next interval that I'm concerned about is between negative 1 and positive 1, because that's the next x value that I have. And then the last one that I have is from 1 to infinity. So let's see what happens with all of these when I plug some values in to the second derivative function. So let's say I do f double prime of, we'll say negative 2. That's within that interval. And when I do that, I happen to get something that is positive. So this is greater than 0. For the next test interval, I'm going to use f double prime of 0, right smack dab in the middle. And this happens to be something that is negative. And then the last one, I'm going to do f double prime of positive 2, and that gives me something that is positive. So what this means is in the first and last intervals, with this guy here and this guy here, in between those 2 intervals, everything is concave upward. And everything within this interval between negative 1 and 1 is concave downward. And then this leads us to talk about what's called points of inflection, which, if you look at the very top, you can see my handwriting, and I abbreviate this as POI, so I don't have to write out the whole thing. But let's take a look at the definition of point of inflection right down here. It says, first let f be a function that is continuous on an open interval, and let c be a point in that interval. Okay, so if the graph of f has a tangent line at this point, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward. And that's the key point of this. A point of inflection of the graph is when the concavity changes from upward to downward, or vice versa, at that point. Okay, so let's take a look at an example to see exactly what they mean. So let's take a look at the first picture up here. I'll just name it number 1 so you can see where I am. But if you can see this, this graph is concave upward, which I will do in blue, all the way up to some point until it starts turning into something concave downward. Okay, where all of my slopes start to get shallower and shallower and shallower until eventually they become 0. So what that means is that this point right here would be my point of inflection. So let's take a look at the next picture. Once again, I'm going to go from concave downward to something concave upward, and the place at which they change concavity is right here, and that's my point of inflection. Notice that they also label or draw the tangent line here. In some instances, a point of inflection happens when the tangent line is equal to 0, or where the slope is equal to 0. That doesn't always happen, but sometimes it will. So let's take a look at the other one, the last one. So here, concave upward all the way up to here, and then it starts turning into concave downward. Once again, since this is where the concavity changed, this is my point of inflection. And with this comes theorem 3.8, which says if c, comma, the function at c is a point of inflection of the graph of f, then either the second derivative is equal to 0 or it does not exist at that point. So if we take a look at graph number 1, let's take a look at this because it shows that the tangent line is doing something like this, right? And that's definitely not 0, and it does seem like it would exist. So why is this considered a point of inflection if it doesn't match this information? Well, so what we want to make sure that we understand is that when I take the first derivative of this function and then the second derivative of this function, that this point, this orange point, whatever its value is at C, okay, if I were to sketch the second derivative of this function, because C is my point of inflection, wherever that is, it would cross this axis at 0 when it's C. That's what that is saying. So just because the tangent line is not 0, or doesn't look like it exists, because it definitely looks like it exists, what it's trying to tell you is that in the second derivative function, this picture over here, that the y value of C, if this is the second derivative, okay, then it crosses the y-axis at 0 at that value. And the same thing with the second two as well. So here, once again, I'm going to kind of estimate where I think C might be. Looks like it's about here. So in the second derivative function, whatever is happening, it crosses this value of C at 0. And this is f double prime again. And the same thing for the last picture. Now, the exception is that f double prime does not exist, period, at that point. And sometimes finding a second derivative is impossible. For example, if we have f of x plus 5, the first derivative of this function would be 1. So then what is the second derivative? And that would be the derivative of any constant is nothing. So we might have a case like this, or what if I have f of x equals 2? Then I could find f prime of x, which would be 0, but then what's f double prime of x? And the question is nothing. It doesn't exist. So that's what you want to look for. Either f prime of c equals 0, or it does not exist at that point. So there's a lot of things to look at, and you have to really take your time. We can take a look at some other information here. So here's the official second derivative test definition. So let f be a function such that the derivative is 0, and the second derivative of f exists on an open interval containing the point of interest, C. So we first want to determine what we already said. We want to see if it's concave upwards or concave downwards. And if this information is true, then we have a relative minimum at this point or a relative maximum at this point. Now, what's important to notice too is that if f double prime of c is equal to 0, the test fails. So what it says is that f may have a relative maximum, a minimum, or neither. And in this case, it says to use the first derivative test instead, because that's what the first derivative helps us do. Okay, so let's apply this with an example and see exactly how we're supposed to use it. So let's take a look at this problem. It says to find the relative extrema for f of x equals negative 3x to the fifth plus 5x cubed. So the very first thing that we want to do is we need to find the critical numbers. And we find critical numbers in our first derivative test. So let's get going. So we first find the first derivative, so f prime of x would be equal to negative 15x to the fourth plus 15x squared. And then we set it equal to 0. And I'm going to factor out a 15x squared. And that's going to be negative x squared plus 1. And when I set all of the pieces equal to 0 here, let's see what we get. So we're going to do this piece, and then I'm just going to rearrange this so that the positive number is first. And what's important to notice is that I can factor this, because it's a difference of perfect squares, as 1 minus x and then 1 plus x. That's important to know. Okay. So we get 3 solutions. My solution over here is going to be x equals 0. My solution for this piece is x is going to be equal to 1. And my solution for this piece is x is going to be equal to negative 1. So those are all my critical numbers. Okay. Now we want to find our second derivative. Okay. So f double prime of x is the derivative of the derivative, which is negative 60x cubed plus 30x. Okay? And so what we want to do with this is we want to use the values that we are concerned about, our critical numbers, because these are either maximum or minimums, and the second derivative test can help us determine which ones they are. So I'm going to get them listed out here in order. So here's x equals negative 1, x equals 0, and x equals positive 1. All right, now these may or may not be minimum or maximum, but this is going to help us determine what we do. So I'm going to take negative 1, and I'm going to plug it in to the second derivative to see if it's at a maximum or a minimum. So if it's concave downward, this should be a maximum. If it's concave upward, it should be a minimum. So when I plug this in to my second derivative, this becomes positive, and therefore this is a relative. Oops, I'm sorry. It's negative. I'm sorry. I'm going crazy. This is negative, and so this would be a relative minimum. When I plug x equals 0 into my second derivative function, I get a negative values, and I just realized that I made another mistake, but let's keep taking a look at this. So if my values are negative, it means it's concave downward, which means I have a relative maximum. So I need to look back over here. One of these is incorrect for x equals negative 1. I didn't mean to make this as positive values, but that means that it's a minimum. If it's concave upward, it means that it's doing something like this. So at this value, at x equals negative 1, that's a minimum. And then for this, it's like this, and so that it's a maximum. So I'm sorry about that confusion. Let's do positive 1. And when I plug this in, I get 0 right on the dot, which means that this test fails, and I don't know what happens there. So it's probably neither. But of course, you can graph these and take a look at the picture for yourself. But this is how we use the second derivative test to help us determine relative extrema, to determine whether it's concave upwards or concave downwards. We can determine a lot of information about our original function by using the first and second derivative test together, and it's really, really helpful when we start doing more applied problems. And that concludes this tutorial.